So I'm very happy with the next speaker because for me, Objective-C is not dead. And the next speaker is going to talk about Objective-C. Probably most of you are still writing Objective-C. You probably know an app that Bruno created. It's called GeniusScan. And he actually spent quite a lot of time trying to optimize this app, especially because the app is quite heavy on processing images. And Bruno is going to talk about that today. And he's going to give us a few hints and a few quite uncommon ways to optimize your app. So welcome, Bruno.
Thank you. Okay, hi everyone. Glad to be here today. My goal today is to talk about optimizing your app's performance. And as an app developer, there are a lot of reasons why you want to make your app fast. First, because you want to be better. But one of the reasons also is as a businessman, it's been shown that a fast app or fast website improves retention and usage. So it's good for you. So there are different ways to go faster in your app. Well, the first way is don't do anything useless, right? That sounds obvious, but just remember it. Second way is to fake it. When you cannot go faster, you can try to make it look faster for the user. That's showing. I guess a progress bar could be one way, but another way, I think Instagram tries to upload photos before even you validate and say send. So in the background, they start uploading, and so it feels like it went very fast. You can parallelize work. Sometimes you can do stuff while the user is doing something. You can do heavy lifting in the background, or you can benefit from multiple cores on your CPU. And the last one, is the one I'm going to talk about more today, is like low-level code optimization. And that's the last, I guess I put it last because you should only do that if the previous things didn't work out well. So let me walk you through like a journey through a real-life, I guess, app. So this is GeniusScan. It's an app that lets users scan documents. So here you see that the app detects the document, then it's going to crop it, correct the perspective, and then enhance it. After that, users can create multi-page PDFs. And we want to go as fast as possible because it's a productivity app, so we want to save time to people. And while launching the last version of GeniusScan 4, a couple weeks ago, one of the things we noticed was a bit slow was the enhance step. So what does this enhance step look like? We have this text, this photo taken with a phone camera. It's pretty good, right? But there are still like it's a bit gray. Contrast is not so good. There are some shadows, some colors on the right. So that's how it looks like after we enhance it with GeniusScan. We just clear the shadow, make it really bright, contrasty. And the steps to do that are threefold. First, we convert the image to grayscale. Then we apply our magic enhancement, and then we return the enhanced image to iOS, to, I guess, the UI. So how does this magic enhancement look like? It's just a very simple call. We call enhance image. We pass an UI image in, and we pass a post-processing. Here it's a black and white post-processing, and that's what we do. So we want to improve the performance of that routine. So one thing I like to do when I do that is just take my problem in isolation. So that's how I will do it. I will create a function with the call I want to optimize. I'm loading an example image. At the end, I'm setting this example image on a UI image view, so I can control that when I make tweaks to my enhancement, I'm not going to break anything. And tests are probably better to check that, but a visual way is also fairly nice to understand what's going on sometimes. And also, I'm going to put a couple iterations here, 100. Gives me more precision when I'm measuring the performance. So what do you do next? You're in Xcode, and you have to remember one thing. It's Command I. With your device plugged in, of course, your real device. You don't want to profile on the simulator, or it's very unlikely you want to. So when you do that, Xcode is going to open instruments. You're going to select the time profiler. You're going to arrive on that beautiful screen of instruments. You're going to hit the record button on the top left. And you're going to act in your app. You're going to launch whatever you want, like to instruments. So in my case, I'm going to tap on these buttons and it's going to just launch the code you saw before. And I just created a big test button for that. And once you're done, you hit stop. And you're here. You have a trace of what happened in your app. And you want to make some sense of this. At the top, you see the blue chart. It's you see the CPU activity. At the bottom, you see a more detailed profile and the sample per function calls. So we want to zoom in on what's important, what's taking time here. So you can hit this little button there, like the secret button I like, and it's gonna take you to the heaviest stack trace. So it means the stack trace where the app spent most of the time. So here I click on my method at the bottom, where I want to zoom in, and it's selected also on the left with the stack trace. Let's clean this up a bit because it's a bit confusing. So what we can do is hit this settings button, and then we hit the hide system libraries checkmark. And here it removes from the stack trace everything that's not ours. Like every iOS framework code is not there anymore. So it's much nicer. So we can zoom in on that. That's our convert method, the just IB action that we called. Then there is the enhance image with post-processing. And here we can see four different steps. The first is the one I mentioned, that converts the UI image to a grayscale buffer. The second is a magic enhancement. And the last one is a convert back to a UI image. What you can notice here is that there are different times. So on the left, you can see that the conversion takes 11.15 seconds. The magic enhancement takes 4.3 seconds. And the conversion back to a UI image, only a couple milliseconds. So the conversion back is okay, it's really fast. The enhancements, it's like 30% of the execution time. It sounds fair, I want to enhance my image. It's normal that I spend some time on the actual enhancement. But like 11 seconds for this conversion from RGB to grayscale, that seems like a lot. So we have found this hotspot. That's the conversion from RGB to grayscale, and that's what we are going to try to look at. So you can double-click on this method in instruments. It's going to take you to the code, so you can see what's taking such a long time. And it's just this code. It's core graphics code. It draws an image in a bitmap context with a color space, gray color space. And that's what converts the RGB image in gray. The question here is, can we do better? Well, of course we can. So we're going to try to rewrite it our way. So just remember, we are going to try to rewrite this method that converts the RGBA image, so red, green, blue, alpha, into gray. So that's an RGBA pixel. It's 3 components or channels. Each of them is 1 byte. It's just a little, you can think of it as a little array of 4 bytes. And so what does that mean? Each byte is between 0 and 255. It's an integer between 0 and 255. That's a gray pixel. So that's 1 byte. And it's just a value between 0 for black and 255 for white. So what we are looking at here is a way to convert this array of 4 components into 1 byte. So we just need to apply a function for that, and that's what our function looks like. The gray, so it's called wide usually, is just this weighted average of the R, G, and B channels. And we forget the alpha channel because we are not really interested in it. All the photos come from the camera, they don't have any transparency. So an image is a sequence of these pixels. So it's a sequence of pixels, so it's a sequence of channels. You can think of it as the interleaved channels. So that's the conversion we want to do. We take our image and we iterate on each pixel and to get, so at the top, to get the gray pixel at the bottom. So we iterate, and in code it looks like that. So that's where it starts to be a bit ugly, but still fairly easy. What we do here, we take each component in the source image, so that's SRC pointer. We convert it to a floating point, and we do our weighted average, and we store it back in a pointer that corresponds to the destination image. So what's the code performance for that? Well, the baseline was there. That's our first iteration, and we instrumented it's about 2 times faster. So it's 2 times faster, it's pretty good. Can we do better? So what you can do is, again, once you've made this change, you re-instrument, and you double-click on this line to see the code again. That's what you're going to see, actually. So here we see that it's sampling, so it's not perfectly accurate, but it sounds like we spend a lot of time on this SRC++, or maybe actually it's a float casting that takes a lot of time. And that's the code we have. Well, can we get rid of the floating point? We are doing this weighted average. Actually, we can. We can by just using integers. So instead of multiplying our data or channels with floating points, we can actually use these integer factors. You have to note that this is going to lead to having a larger integer. And what we do at the end, we divide this integer by 256 to come back to the 1 byte component of the gray channel. And we can divide by 256 by doing a right shift of 8 bits. So what does the performance look like? Well, it's 4 times faster than the original version. That's quite good, actually, by just making a little change. Can we do better again? Yes, so there is a way to do faster. So we're going to talk a bit about vectorization. So what is vectorization? Your CPU usually can do 1 operation at a time. But modern CPUs, modern as in like for the past several couple years, have vector instructions. And these vector instructions can work on parallel lanes. They work on basically vectors, so it means they work on arrays. So instead of doing an addition of 1 integer with another integer, you can do an addition of 8 integers with 8 other integers in parallel. Or I mean, 1 by 1, but in parallel. So you do 8 operations in parallel. And that has nothing to do with multiple cores. It's just on 1 single core. So that's how it's going to look like now. We can apply a function to an array of pixels, of RGBA pixels, and get an array of gray pixels. That's basically the same formula we used before. And that's how the code looks like. Okay, so it's a bit more complicated, but there is not much, to worry about. It's basically here we are using multiplication, additions, shift, but instead of using the regular operators you know from C, we use these functions called intrinsics. They are available in headers in the iOS framework. And so these intrinsics allow us to work on 8 by 8 pixels, basically. That's why, actually, at the end, you notice that instead of increasing by one pixel at a time, we are going to skip 8 pixels at a time because we have treated 8 pixels in 1 iteration of the loop. So what does it look like? Oh, I guess this guy loves charts. No. That's how it looks like. It's 11 times faster. 11 times faster, that's the baseline. That's actually really good. And now we can wonder, can we do better again? Well, maybe. That's where we can look into assembly code. So, I mean, do we really want to do that? Yeah, well, let's try, That's how it looks like. That's how it looks like. Also, here it's one screen, but it's actually several hours of trial and errors. It ended up working. It's basically the same code as before, but it's rewritten with assembly instructions. I'm not going to detail that, but you will notice one thing first, is that you have two versions, right? There is an ARM64 version and an ARM Neon version. That's because the assembly instructions for these two platforms are not compatible. So you need to write two versions. That's actually quite annoying and making it take more time. ARM64 is actually I'm not exactly sure, but it's iPhone 6 and later, something like that. What's the performance of this? That's interesting. We try it, and it's 22x. So 22x faster than what we just had before. That's pretty cool, actually. But just let's reflect on that. What did we change? We just rewrote the same code, the same exact code, using the same exact instructions, but in assembly. We did the job of the compiler. And maybe we expected a little speed up compared to the version before, because maybe the compiler was not perfect, but it's 2 times faster than the previous version. That sounds a bit crazy. Well, it turns out it is crazy. It was a mistake. So the story here is that instruments is sometimes a bit finicky. And to go faster, I had just measured the time difference with the previous iteration using NSLog statements, printing the time. I had run my code, not thinking about it, using command R rather than command I. So I ran it in debug rather than in release mode. And that makes a lot of difference. Because my assembly code was fairly optimized. But the code from the vectorized version was not optimized at all by the compiler, because it was in debug mode. So in debug mode, the compiler cannot do optimizations because it would lose track of where to stop, and it cannot remove any instructions for you. So it's going to leave everything. It's not going to be optimal. So that's one lesson. First is, if you want to profile something, don't use debug statements like that. You have to use instruments, and the shortcut is command I. So that's how it looks like actually when you profile it. It's the same time as the vectorized version. So we spent a lot of time writing these two different assembly versions. It was a lot of mistakes. It's not portable at all because it works here on Neon ARM64, but it doesn't work on a lot of other platforms. It's very hard to maintain. I don't understand this code anymore. I would need a week to understand it again. And compilers aren't stupid. So you don't need to go so deep, so low level on your code generally. Going to assembly is not a good idea. So let's just forget this. And that's our best version so far. It's 11 times faster than the original. It's actually a good speed up. Are we satisfied? So let's check. The performance is 11 times faster. So that's really good. Is it maintainable? Well, I think if someone reads it later, they can figure out what it does. It's not easy, but it's better than the assembly version. And is it portable? Neon instructions are available on all fairly recent hardware, iOS and Android actually. So that code would be portable on Android, except on Android x86, which is another version, but we can talk about that later. And the intrinsics we have been using, so these little functions, they hide the difference between the ARM64 and the ARM7 instructions. So that's pretty cool. I think I'm fairly satisfied to make this trade-off between maintainability portability for an 11x speedup. Testing now. So we want to write some tests. And we are gonna try, like we have improved this with one single image. We are gonna try with a different input image. And what happened here? We get a crash. And that's interesting. We actually hit an edge case. So the mistake number 2 is that when you optimize, you also need to think about all the different edge cases. Here, our edge case is something called unaligned image. Most of the images have a width which is a multiple of 8. So when we process the pixels 8 by 8, it's perfect. Everything goes well. But if you crop an image, for instance with GeniusScan, the image width is not necessarily going to be a multiple of 8. It can be smaller. It can be a multiple of whatever. But that's fairly uncommon, right? Most of the photos you take from your camera are like 248, 4096 pixels wide, and so. So that's why we didn't hit that case with our little test. So that's one edge case. The other edge case we can think about is here we get a RGBA input image. That's the images you get out of the iPhone camera. But what if we got a RGB image? What if we got a BGR image or a BGRA, which you can get on Android? It's just the channels in a different order. Well, our code wouldn't work. So how do you deal with that? I think one way you can deal with that is that you make a check. You check if the image is aligned. You check if it's RGBA. Then you can call your very fast routine, the neon routine. And otherwise, you can fall back on the initial implementation. I think that's actually a satisfying solution. In our case, we want to go fast for most of the cases. If for some of the edge cases, we have to fall back to a slower implementation, I'm fine with that. So what are the trade-offs? The trade-offs are portability, and that's something we have shown that, for instance, assembly wouldn't work on different devices, on for instance, Android x86, and we need to deal with that in different ways. Another trade-off is maintainability. Do you really want to go through making your code more complicated to go faster? Do you go fast enough that you can afford like this maintainability decrease? And you need to think about handling all the edge cases. That core graphics implementation at the beginning it's 11 times slower than ours. But why? Probably because it deals with all these edge cases. And by dealing with all these edge cases, it has to make some trade-offs on performance. So that's the important question to ask yourself when you do this kind of optimization and when you start spending time on something. Is it worth it? And for instance, for the assembly version, it clearly wasn't worth it at all. So what are the takeaways of this? The first thing is that I would recommend not guessing. It's easy to guess what is slow, what is fast. You can easily assume that Apple's code is the fastest because it's good. But maybe in your case, it's not going to be the case. So don't measure the timings in debug mode. It's not going to lead to an accurate representation of what happens in real life. Use instruments. I think instruments takes a little time to get familiar with, but it's actually really good, particularly for time profiling and memory leaks as well. So this common I shortcut is something to remember. Focus on the hotspots. In our case, we noticed that this conversion in gray from RGBA to gray was taking like 70% of the time of our enhancement routine. The other part was taking 30%. You generally want to focus on what's taking most of the time because that's where your best time performance gain is going to be. What can you look at when you are going through this performance optimization at the low code level? What can you look into? You can look into removing superfluous instructions, anything that's not needed, or any I guess slow spots. An example here I didn't mention is I do this right shift to divide by 256. It's much faster to do a right shift than to do a division. And sometimes the compiler will also do it. Like usually, if I divide it by 256, the compiler would automatically replace it with a right shift. So, but that's this kind of thing that make you go faster. And using vectorization. And vectorization, some compilers do it, but it's also hard for the compiler to know if they can do vectorization. So that's why you have to do it by hand sometimes. Iterate and be ready to step back. Like the assembly version, I mean, it was as fast as the vectorized version, but clearly, even if I had spent a week on it, it was not worth keeping in the app. I mean, it would have led to a lot of trouble, bugs, and problems later. Don't forget the edge cases. It's easy to do something that goes fast, but you need to think about these edge cases, and the best way is probably to write like the tests before to think about them. And always ask yourself, is the added complexity worth the trouble? And thank you.
Thanks very much. I really like the fact that you were not ashamed of saying that you made a mistake with trying to profile something that is built as debug mode in debug mode. Mm-hmm. And that's great, because I mean that's the kind of mistake we all do.
Yeah, sometimes you get caught up in it, and you just don't think very clearly anymore. You know? Yeah,
and if you see that, you say, "Oh, that's a rookie mistake," but like you do it still. So that's kind of interesting to see that. And did you try to do some multi-core optimization, like parallelism?
So you can do some parallelism. In this case. I mean, you have some trade-off with parallelism and multi-core, is that you need to load the data on multiple CPUs. You need to be able to split the data on the different cores, and sometimes it's not worth the time. So I think if we, like here, the RGBA conversion is very simple. It's just 3 multiplications and 2 additions. It's probably not worth splitting on multiple CPUs. If you were doing something more complex, a more complex filter on the image, it would make more sense.
And like on the next step, like the magic recipe, like do you do some?
No, we don't. No, we don't.
And did you try to see if it would be worth?
It could be. We didn't try, so far. But it's actually fairly fast for what it's like like here it takes 11 seconds, but that's for 100 iterations. So.
Yeah, so that's kind of. And why did you choose to actually go in that direction? Like. Some of the time, like we want to optimize, and then we go straight to optimization because we're engineers and we like doing optimization sometimes. But I kind of feel that it's kind of dangerous to optimize too early. And what triggered the optimization mission on your case?
It's a good way. I think that's part of it is because I enjoyed doing it.
Okay.
But no. But I think it's important also. In our case, in the last version of GeneScan, we are doing like real-time scanning, and so it's important that it goes as fast as possible. That doesn't need to go as fast as 1 frame, like 60 frames per second, but it has to go fairly fast.
And like we see your magic effect right on the photo, right?
Yeah.
Oh, that's nice.
Yeah. Did you try to use Xcode to measure?
No. I actually, I think I'm not very familiar with Xcode, but one thing I think it's interesting is that you can run it on continuous integration to see if you have regressions in timing. The problem is that continuous integration and actual devices is not super, easy to do. I don't know if you can do it. You have to keep devices plugged in.
Yeah, that's nice.
So in the simulators, this wouldn't be as interesting.
Yeah, of course.
Or on a Circle CI server that we don't control. We don't know if it's slower because something else happened.
Yeah, sure. Did you have any benchmarks on Swift? Did you?
So we didn't measure with Swift. It's interesting. So Swift has actually it's called SIMD instructions as well, support. I think in the Accelerate framework you can import SIMD, like a SIMD framework, and basically all the array operations have been rewritten to do with vector support. So that's gonna help. I didn't try it. One thing which is really good about C. Like some people say that C is the fastest languages. Some others say no, it's not. One thing is good, which is good about C, is that the translation from C to a language machine is fairly direct. So when you manipulate a C pointer, you basically manipulate a memory address, and you know what. You have an idea of what you are doing.
On the slide, like when we see your vectorized code, it's almost assembly. Like you really manipulate.
The mapping is very close.
Yeah. So that's also very nice. And you say that it's not worth it, implementing in assembly, but I'm sure it's so cool and so swag that it's.
Yeah,
it's
I was super.
Especially talking about that here, and
I was super happy about the 22x improvement, but sadly,
too bad.
I mean, you made assembly look so simple that I almost want to do assembly all the rest of my life. But
don't do that.
There is actually one moment in the presentation where you are actually saying that that instruments was painfully slow, and do you have some idea on why it was slow? Because you also said that you used the headless mode, and I thought that maybe sometimes instruments is quite slow because it needs to record a lot of things and display them at the same time. But even with the headless mode, it was painful.
More than slow, I think that it's just more like finicky. It's just sometimes you do command I is really cool, but sometimes it launches instrument but does not load the symbols for your app, so you need to relaunch it again. Or you can do file symbols, find the symbols. I think because it needs Spotlight to index something between Xcode and instruments. So that's a bit painful, and at some point, when you iterate quickly and fast, you don't want to deal with that, and that's why I made the mistake of running it in debug mode.
Yeah, totally get that.
All right.
Did
you try any of those low level tools like dtrace or gprof or stuff like that?
No, actually, I've seen there is a
good transition
tomorrow. No, I have not. I don't know actually much about it. So
okay.
Curious.
So thank you very much.